Hi and welcome. I have made two other videos about the Monte Carlo method, but I found this interesting brain teaser in mathematical paradox that I thought would be interesting to prove using Monte Carlo simulation. In this video, I'm going to show you how to simulate and prove the Monty Hall problem using random sampling in Matlab. First of all, disclaimer, I'm not a mathematician or anything, so I don't really know the underlying proof behind this problem, but I will try my best to briefly explain the setup, and if you're interested, I would suggest watching a video that was put out by Numberphile. The problem goes, imagine you're a player on a game show, and you have 3 closed doors before you. 2 of the doors have goats behind them, and one of the doors has the winning prize, a car. You choose one of the doors that you would like to open up, but before you open the door, the host will open one of the other doors that has a goat behind it. And you are given the option of keeping the door you chose or changing to the other door. And the question is it ever to your benefit to change your choice? Most people would say no, because you obviously have a 1/3 chance of winning a car when you first choose. And you would think that even after one of the doors is opened up, you would at that point have a 50% chance of winning. But as you'll see in the simulation, this isn't actually the case. The mathematical proof in simulations show that if you always keep the first door you chose, you'll win 1/3 of the time. But if you always change your answer to the remaining door, you will win 66% of the time. How can changing your answer last minute increase your chance by double? So this is not a complete proof of the problem, but this one picture I want to show you kind of helps you intuitively see what's going on. So you first choose one of the doors. There's a 1/3 chance of the car being behind door 1, and there's a 2/3 chance of it being behind these 2 doors. And say you chose door 1, and the host opens up door 3, and the chance of door 1 being a car is still 1/3. But now for the door that was opened, there's a 0 chance of it being a car. So the remaining 2/3 has to go to this second door. So that's why if you change your door to number 2, then you will have a 2/3 chance of winning. Again, this is not a full proof of the problem. If you are actually interested, Numberphile kind of goes over a little bit more into detail about what's going on. So I would suggest watching that and then coming back to this video. So first we're going to start off by making an array called doors, and we're just going to have numbers 1, 2, and 3, and this array will represent the doors in the game show. And now I'm going to randomly shuffle what is behind the doors by using randperm, which this function will just produce a random permutation of the numbers 1, 2, and 3, just like this. So what I'm going to do is set the goat to be elements 1 and 2, and then set the car to be element 3. And that's exactly what these 2 lines are going to do. Then we're going to randomly pick the player's choice by using rand_i, and what this function call will do will just produce a random integer between 1 and 3. So now we're going to go back to the doors array and take player choice and set that equal to 0. So for instance, in this call down here, the player chose door 1. So we're going to say doors array, we're going to set this entry to 0, meaning that this door has already been chosen. Next, we're going to do the similar thing to the host's choice, again using rand_i. And so it makes sense that the host cannot choose the same door as the player, and the host can also not choose the same door that the car is behind. So we have to have some loop that is going to test for this. So what we're doing here is saying while host choice is equal to player choice or host choice is equal to car, we're going to again pick another random number. And then we're going to do a similar thing and remove the host choice from door by setting it equal to 0. And then finally, we're going to say for I if door I not equal to 0, we're going to call this variable remaining door, and that's equal to door I. So this function call, when we call this function here, we're going to return what the remaining door is. So I'm going to make this block of code be a function. I'm going to indent it and put the function header, which is just going to return the player choice, the host choice, the car, and the remaining door. And I'm calling this function Monty Hall sim, and it takes in no param. And then you need the end, and then save as the name of the function. And then once that's finished, we're going to open up a new script. And in this script, we're actually going to use the Monte Carlo method to call a large number of these rounds. So first some housekeeping. We're going to clear all and clear the screen. And I'm going to make a variable called total runs, set that to 100. And then I'm going to make a variable called probability underscore CD for change door zeros. And this will just make a 1 by 100 array of zeros. And then we're going to do the same thing for the probability of keeping your door. And then we're going to do the same thing for keep door. So you're going to make a for loop that goes through 1 and with steps of 10 and total runs times 10. So what this for loop will do is we're going to call this Monty Hall sim function, and we're going to call it a bunch of times until we've hit total runs times 10. And I'm going to make a variable called wins underscore change door, set that to 0, and wins underscore keep door. And we're going to have another for loop, go from 1 to I. I is going to say how many times we're going to run a single round of the game, and then we're going to add them all up and plot it. So here we're going to do the function call, and we're going to set it to all these variables. So we're going to test if the remaining door that the player did not choose, if that's equal to the car, then we're going to add up wins for if we had changed the door. We're going to do the same thing but for keep door, and then end that, and then say prob change, go to wins underscore change door divided by the number of times we ran the rounds. So we actually need to keep a variable up here called t. I'm going to set it start it as 1, and then after each for loop we're going to increment it, and then I'm going to say change door t is equal to the probability of that change door. And so here we're basically making an array of the chances that we have that we want, and this is going to make it easy to plot. And then we're going to do a similar thing for keep door. Okay, so that's pretty much all there is to it. We're making these arrays that store the percentage of wins that we had for each situation where we changed the door or we kept the door. And then I'm just going to copy and paste this block of code, which is just going to plot it, and we can see what it looks like when it's plotted. So we just save it. I'll call that main. So I made a mistake here on line 21. You want to make sure you divide the wins of keep door by I, the number of rounds, just like we did in here for change door. And when that finishes running, this figure will pop up, and on the x-axis we have the number of runs. So we went from 1 to 1000, and on the y-axis we have the probability of winning, and you can see that the blue represents the change door situation and red represents the keep door situation. And I plotted these dotted lines of 66% for change door and then 33% for keep door. And you can see that each of these points, as the number of runs increases, they start converging towards these horizontal lines. And this kind of proves the Monty Hall problem. You can see that we have about a 66% chance of winning if we were to change our door versus if we kept the door. Okay, that's pretty much it. Again, I made 2 other videos on using the Monte Carlo method in Matlab. If you're interested in those, go check them out. Otherwise, thanks for watching.